In the world of AI language models, one concept shows up again and again: the token. Whether you're working with GPT, BERT, Claude, or any other large language model, tokens are at the very core of how these systems understand and generate language. But what exactly is a token? And why does it matter so much in the context of artificial intelligence? A token is a unit of text that a language model processes. It could be a word, part of a word, or even just a single character, depending on the tokenization strategy being used. For example, in a sentence like "artificial intelligence is powerful," some models may split this into tokens like "artificial intelligence is" and "powerful." Others may break it down even further into subword units like art, official, intelli, gency, or into character-level tokens such as A, R, T, I, and so on. Tokenization is essentially the first step that transforms raw text into something the model can work with. Since these models operate on numerical data, tokens are mapped to numerical representations, often called token IDs. These IDs correspond to vectors, long arrays of numbers that serve as the input to neural networks. Different models use different tokenization methods. Early models like Word2Vec operated on word-level tokens. This approach worked well for many applications, but ran into problems with rare words, misspellings, and morphologically rich languages. Subword tokenization became a popular solution. Tools like byte pair encoding, BPE, word piece, and sentence piece split words into smaller pieces, subwords, that strike a balance between handling common words efficiently while also being able to compose meaning from rare or unseen terms. For instance, in BPE, the word unhappiness might be broken down into tokens like un, happy, and ness. This method reduces the size of the vocabulary that the model needs to learn, while also improving its ability to deal with linguistic variation. It's one reason modern models can generalize so well. Tokens are not just about input, they also govern output. When you ask a language model to generate a response, it generates one token at a time, predicting the most likely next token based on context. This process continues until a stopping condition is met, such as reaching a maximum token limit, encountering a special stop token, or completing a syntactic structure. This has practical implications. Most API providers, like OpenAI or Anthropic, charge users based on the number of tokens processed, both input and output. So understanding tokenization isn't just academic. It affects cost, speed, and usability. A prompt that looks short in words may be long in tokens, especially if it includes a lot of formatting, code, or uncommon characters. Moreover, the token limit of a model determines how much information it can see at once. A model with a 2048 token limit can't process a document longer than that window unless you split it or summarize it. Newer models like GPT-4 Turbo or Claude 3 Opus support larger contexts, up to 128K tokens, enabling them to handle entire books, research papers, or legal contracts in a single pass. But tokens also represent a fundamental shift in how we think about language. Instead of treating language as a collection of discrete, grammatical rules, tokenization treats it as data, patterns of characters and symbols that can be learned statistically. This data-driven view is what enables machines to predict language with such fluency and creativity. And yet, this token-based approach has its trade-offs. While it's efficient and scalable, it also fragments language in ways that may lose some meaning. Sarcasm, metaphor, and cultural nuance often span multiple tokens, and current models sometimes miss the bigger picture. Efforts are ongoing to build models that handle entire sentences or paragraphs as coherent units, moving from token-based analysis to semantic understanding. Still, tokens remain the currency of language models. Everything from model training to inference to fine-tuning revolves around them. Token counts influence memory usage, training time, model size, and performance metrics. They define how models chunk reality into bits that can be processed, predicted, and reproduced. Another fascinating aspect of tokens is how they intersect with language diversity. Tokenization strategies can have unintended consequences depending on the language. In English, splitting by subwords works relatively well because the language is structured with prefixes, suffixes, and compound words. But for languages like Chinese or Japanese, where words are not separated by spaces, tokenization becomes much more complex. In such cases, models often rely on character-level tokens or need specialized pre-tokenizers trained on that specific language structure. Without careful handling, tokenization can skew model performance, favoring certain languages or dialects. This raises important questions about linguistic equity and inclusion in AI development. Are models trained on a fair representation of languages and cultures? Do tokenization schemes inherently bias the system toward majority language speakers? In response, multilingual tokenizers, like those used in multilingual BERT or XLM Roberta, have been designed to work across many languages. They utilize shared subword vocabularies so that the model can process input from different language families. This allows for cross-lingual transfer, where a model trained heavily on English can still perform reasonably well on French, Hindi, or Swahili. But even here, token counts vary dramatically by language. A single sentence in English may be 10 tokens, the same cent. Tokenization also plays a vital role in model interpretability and alignment. During the training phase, language models are optimized to predict the next token. The loss function, commonly cross-entropy, calculates how far off the model's predicted token is from the correct one. This feedback loop is what shapes the model's parameters over millions of training steps. Each token prediction acts like a micro-decision, nudging the model toward fluency or failure. Understanding which tokens the model is focusing on can also aid in interpretability. Tools like attention heat maps show which tokens are influencing predictions the most. For example, in a sentence about climate change, the model might weight warming, emissions, and carbon more heavily than auxiliary words like is or of. These visualizations offer insights into how models prioritize information and can help debug or audit behavior. When fine-tuning models for specific applications, say legal document summarization or customer service bots, the choice of tokenizer and token limit becomes a crucial design consideration. If a model is consistently truncating important information due to token limits, its usefulness diminishes. Engineers often experiment with prompt formatting, prompt compression, or hierarchical summarization to work within these constraints. Even in prompting strategies, tokens matter. Few-shot learning, zero-shot learning, and chain-of-thought prompting are all affected by how many tokens are consumed. A well-crafted prompt may fail if it exceeds the context window or uses inefficient wording. Skilled prompt engineers learn to write for token economy, conveying maximal meaning with minimal token cost. Tokenization also defines how models handle code. Programming languages, with their symbols and syntax, are tokenized differently from human language. Specialized models like Codex or Codalama use tokenizers designed to parse brackets, keywords, and indentation effectively. Accurate tokenization is vital for understanding logic structures, maintaining code coherence, and avoiding hallucinations. As models grow larger, tokenization continues to evolve. There is growing interest in dynamic tokenization, adaptive schemes that vary token granularity based on context. Instead of fixed-length subwords, some approaches explore content-aware segmentation, which could improve both efficiency and comprehension. But no matter how advanced models become, their foundation still rests on tokens. These tiny slices of language represent a bridge between human expression and machine understanding. By dissecting language into tokens, we've given machines a way to learn from us. And by learning how they process tokens, we gain insight into how machines think. So what is a token in AI language models? It's more than a piece of text. It's the atom of machine understanding. Every prediction, every conversation, every poem generated by AI begins with a token. And every time you type a prompt, tokens guide how your words are interpreted, processed, and transformed into a response. As we continue to build and interact with language models, knowing how tokens work empowers us to design better prompts, manage resources more effectively, and build systems that truly understand human language. Not just in fragments, but in meaning. Tokens may be small, but their impact is vast. In the world of AI, they are where language begins.